Okay, so welcome to the next in our series of screencast videos for Math 1410 Linear Algebra. Um, this is going to be the first video covering material from Chapter 3 on vector geometry. So we're going to start out with Cartesian coordinates, and we've just finished the chapter on complex numbers, so we have some comfort level already with Cartesian coordinates in the plane. We had this picture for complex numbers where we have this complex plane, right? So a complex number x plus iy, we think of x and y as coordinates in a two-dimensional plane. And so we have this picture already that we're kind of used to for the complex numbers, but we'll recap how things work in R2, the usual sort of system. Pairs of points. So just as a reminder, you start with the real number system, and we've already gone over the fact that there's some difficulty in giving a careful definition of the real numbers, and we're not going to bother getting into the technicalities of that here. But you picture the real numbers as this continuous number line. There's no gaps in there. You can, as you move along, as you move from point to point to point, every single point on that line corresponds to some number. And there's no limit. You can keep going forever. If you go off to the right, you sort of head off towards, positive infinity. If you head off the other direction, you're off to negative infinity. Of course, plus and minus infinity, these are not real numbers. They're just, this is a way of indicating that there is no end to the real number system. You can increase them forever and ever. You can get bigger and bigger and bigger. There's no limit to how big you can make your numbers. All right, and so of course all the integers are in there, all the rational numbers are in there, but roots are in there, numbers like pi, e, all these numbers are there in the real number system. Anything that you can write down with a decimal expansion is going to give you a real number. Okay, and then of course so the Cartesian plane, the one that we're familiar with both from high school and from working with our complex numbers, the set of all ordered pairs. So as a set, we haven't assigned any geometry to it yet. We just simply make this definition right here. Right, so we say it's a set of all ordered pairs. And by ordered, what we mean by ordered is we mean that, the pair xy is not the same thing as the pair yx. Well, unless x is equal to y, right? So changing the order changes the element of this set, changes the point. And the way we like to visualize these things is we kind of think of each of these two real numbers as giving you a point along some number line. And so we have two axes, right? You have an x-axis, you have a y-axis, and the convention here is that the x-axis increases from left to right, so this is the positive direction, this is the negative direction. The y-axis increases from bottom to top, so this is negative, this is positive, and they meet at the common 0. So where they cross is the 0 value for both x and y. And so if somebody hands you an ordered pair, they give you something like, say, the point 2, 3. This is telling you that x is equal to 2, so you kind of go, okay, 1, 2, there, x is equal to 2, y is equal to 3, 1, 2, 3, right? But the way you actually identify that point is you kind of draw you've got sort of 3 of the 4 corners of a rectangle, so you complete this rectangle, and you kind of draw things out like that, and that remaining corner of the rectangle, you mark that spot and you label that as the point 2, 3. So you think of these two numbers 2 and 3 as giving you the measure of how far away that point is from each of the two axes. Right? And of course you can see this idea that this ordering matters, because if we switch to, say, the point 3, 2, if we want to do the point 3, 2, well, then we'd have to go, x is equal to 3, so we go 3 units out in the x direction. We'll only go 2 units in the y direction, and our rectangle then would look like this, and we would have this guy here, the point 3, 2, and we can see that indeed that is not the same point as the point 2, 3, right? So this ordering matters. So what we do now is you take this idea and you extend it. You say you don't have to stop with 2 variables. You could extend to 3 variables. So you say R3, x, y, z. You add a z coordinate. and so on. But you don't actually have to stop at 3. You can consider any number of variables. So we can define in general the set Rn to be, so what these elements, they kind of have a funny name. These guys are sometimes called ordered n tuples. Um, so this n tuple is some attempt at generalizing the language of double, triple, quadruple to n tuples, where n could be any positive integer. At some point, you run out of words for this, and so the ordering again means that if you swap any two of these n numbers, then you get a different element, right? So um, you know you've got a first coordinate x1, second coordinate x2, third coordinate x3, and so on. And so the order matters, right? If you change any two of the positions, you change the point that you're talking about. And now, of course, if you're dealing with 4 or more variables, there isn't really a picture you can draw. You can't picture things anymore. You can't visualize it. But that kind of limitation, of the human brain to visualize things beyond 3 dimensions is not a limitation that's shared by the mathematics. The mathematics works just the same, no matter how many variables you have. And you do want to consider more than 3 variables. There are lots of practical problems where you might be dealing with hundreds or thousands or even millions of variables. Think of problems coming from economics, from finance, even from physics or chemistry. You might be dealing with large numbers of variables, and you want some mathematics to be able to describe these things, and so you have to move to these sorts of sets. Now, in 3 dimensions is the only one we haven't drawn, which we can draw. So in R3, the picture for R3, we get something that looks like this. So the way you kind of try to visualize R3 is you imagine you're looking at like the corner of a room. So you get something like this. And so these 3 lines, these 3 edges that kind of converge at one point, this is how you represent the 3-dimensional coordinate system. And so you think of these as your coordinate axes, label them x, y, and z. This is not the only labeling you could choose, but it's usually the one that we'll work with. It's the most convenient one that you can work with. And we draw this so that what we've drawn here are the positive x, y, and z axes. And of course these do extend in either direction. So the x-axis goes off that way, and the y-axis goes off that way, and the z-axis goes off that way. We often just draw them like so. And so of course we, just as with R2, we require that everything meets at the common 0. So this point, is the point 0, 0, 0. And then every other point can be plotted with reference to these axes. The only problem is that when you try to plot a point, you're trying to draw a 3-dimensional picture on a 2-dimensional surface, and this generally ends badly. So if we have a point, right? So here's a point. We can describe that point by these coordinates x, y, and z. But how do you actually kind of picture this location in space? If you've got some nice 3D graphics software, you might be able to set up something where you can input values for x, y, z, and then rotate your point of view and look at it from different directions and get some idea of what you're looking at. If you're trying to draw this by hand on paper or on a screen, what you can do, one way you can kind of get around this is you can imagine that down here is maybe the shadow of that point on the xy plane where z is equal to 0. So you can think of, there's this copy of the xy plane sitting here, right? And so that's where that drops onto. And then of course, once you've got that point in the xy plane, you can situate it with respect to the x and y axes. So you can drop this over, and so here would be your point. So this would be, x, 0, 0, and you could go along this way parallel to the x-axis until you hit this point on the y-axis corresponding. So this would be the point 0, y, 0. The z coordinate is a little trickier. Where does this thing, where's the shadow on the z axis? Well, what you can do, just like in R2, we kind of visualize things using rectangles. Well, in 3 dimensions, the three-dimensional version of a rectangle is a box. So you've got part of a box sitting there already, so we complete this box. So we kind of draw the remaining sides, and we get something like so. And then you can see, okay, there's this corner of the box that actually hits the z-axis, and so the point 0, 0, z is sitting right there. And now you've got this kind of three-dimensional box there, which lets you kind of get some idea of how you would visualize a point in three-dimensional space in this sort of two-dimensional drawing. Okay, now from here we want to talk about distance. And we've talked a little bit about distance in the context of complex numbers, because we've talked about, the modulus of complex numbers, is the distance from a complex number to the origin. And you can even talk about distance in one dimension. So the absolute value function, and just to remind you, if you haven't seen the absolute value function before, the absolute value of a number is, well, if you give it a positive number, nothing happens. So if a is bigger than or equal to 0, it just gives you back a. If you plug in a negative number, it says, I don't want a negative number, I only want a positive number. So it switches the sign. So if a is less than 0, it gives you minus a, right? And now remember that if a is negative, the negative of a negative is going to be positive. So minus a would be bigger than 0 in this sense, right? So the absolute value is basically telling you how far away any real number is from 0, right? And then if you want to figure out the distance between two other real numbers, well, you take their difference, right? The difference tells you how far apart those two numbers are, but the difference could be negative, and you'd like distance to be positive. The absolute value guarantees that outcome will be positive. One way to write the absolute value is as the square root of a square. Because notice that if you take, say, the square root of, let's say I take minus 2, I square it, and then I take the square root. Well, squaring minus 2 gives me plus 4, and the square root here always denotes positive square root. So you plug in minus 2, you get out plus 2, which is minus 2, right? So 2 is equal to minus 2. It's consistent with this definition of the absolute value. And so in 2 dimensions, we know that the Pythagorean theorem holds for us, and the idea is if I've got 2 points in the plane, if I've got an x1, y1 over here, and I've got an x2, y2 over here, I want to measure the distance between them, and so what I do is I kind of, I can draw in a little right-angled triangle like so, and this is the distance we're looking for, the length of the hypotenuse. But we know that the length of the base here is just going to be x2 minus x1, right? The difference between the x coordinates. The height is going to be y2 minus y1, right? As I've drawn it, x2 is bigger than x1 and y2 is bigger than y1, so I've done x2 minus x1, y2 minus y1. But of course, if I'd done it the other way around, I would get the negative of what I have here, but when I square things, that negative goes away, and so we get this distance formula right here. And it's coming exactly from the Pythagorean theorem. All right. Now, what if you want to extend this distance formula to higher dimensions? Well, in 3 dimensions, you can actually show that that the same definition works. So, if you have one number, you square it, and then you take the square root. If you have 2 numbers, you take the sum of the squares, and then you take the square root. If you have 3 coordinates, well, now you have 1, 2, 3 squares. You add them up, and then you take the square root. And then in Rn, you just kind of, you go with it and you say, okay, the distance between, well, now things get a little bit harder to kind of, specify, but maybe I have something like, the distance from A1, A2 down to AN, and, B1, B2 down to BN, and you take the difference between the A1 and B1s and the A2 and the B2s, and so on down to the last coordinate. And then you take the square root of that whole thing, and that should give you the distance, right? You just kind of assume that this pattern continues. How do you see that the pattern should continue into 3 dimensions? It's a little bit tricky, but let me sketch things out. Well, let me sketch things out in the case that we're just dealing with distance from the origin. So from 0, 0, 0 to a point x, y, z, because that's a little bit easier to draw. So the idea is we do the same kind of trick we did previously to kind of locate our point. So we drop that point down onto the xy plane. Here's our distance xy0, and then we say, okay, well, we've got 2 sides here. The length of this side is just z, right? Because this is just, from the xy plane up to the point xyz. The difference between the two is just the change in the z coordinate. Now, this distance here, we can think of that distance as being measured in the xy plane, right? X, y, z, those are our coordinates. And so we can use the distance formula from the previous slide for distance in R2. We can think of this xy plane as a copy of R2. And so this distance should simply be, square root of x squared plus y squared. Using, if you like, it maybe doesn't quite look like a right-angled triangle, but, this is a right-angled triangle here, where this side has length y, this side has length x, and so Pythagoras tells us that this side should have length x squared plus y squared. But there's one more right-angled triangle, which is this guy. And again, because we're doing perspective drawings, it doesn't quite look like a right-angled triangle. But it has to be, because that vertical line, right, that's landing straight on the xy plane. So that's a vertical line meeting a horizontal plane. Those definitely meet at right angles. So that's a right-angled triangle. This is the distance that we're interested in. And, well, we can see that one of our sides is this square root here. The other side is this guy. And so the distance squared is going to be square root of x squared plus y squared plus z squared, which is just x squared plus y squared plus z squared. And so taking the square root, and of course distance should be positive, you take the positive square root, that gets you to this distance formula here. Okay, so that's it for the Cartesian coordinate system. We'll be moving on to vectors in the next screencast.